Okay, so welcome to Guided Study Group Week 6 for Math 140. This week we're just gonna continue the materials for midterm 2. After what we've learned last week, which is linear approximation and the local maximum and local minimum, and also the the general idea of extreme values. So now we'll be working on section 3.2 and 3.3. So it's going to be when we're going to use Rolle's theorem and the mean value theorem to kind of help us to see if there's any special kind of general idea on what is the slope of the what is the derivative of that function on say a specific interval before we can actually graph it in 3.5. But these 3.1 to 3.4 is where you kind of try to obtain as much information as possible from the first and the second derivative test. So let's get started. So we have first is Rolle's theorem and the mean value theorem. So before we get started, I would say the Rolle's theorem is just one of the specific case of the mean value theorem. So with that memory in mind, and if you remember the mean value theorem, then it will be much easier for you to come back to the Rolle's theorem. So the Rolle's theorem says if you have a function f that satisfies the free hypothesis that is continuous and differentiable on that specific interval, and you have the value at the two end, fa and fb equal to one another, then there'll be a number c in the middle such that f prime of c equal to 0. We also have the mean value theorem. So it's it is a function that satisfies only two hypotheses, the continuous and differentiable hypothesis, but then it's more general in the sense that it say there exists a number c from a to b, such that f prime c is equal to fb minus fa divided by b minus a. Now, why did I say Rolle's theorem is kind of like the specific case of mean value theorem? It is when you have this extra conditions when you have fa equal to fb. So having said that, we also have other theorems say if you have f prime of x equal to 0, so the derivative of the function is equal to 0 for all x in an interval, then you have f is a constant. So very easy to visualize if it's equal to 0. It's just gonna be a straight line. If it's a curve, then there will be points that you have the slope of the derivative not 0. So f prime x cannot, so this part is not satisfied. So there's only one case where you have, if you have f prime of x equal to 0 for all x on an interval, then you have f is a constant. We have a corollary, but which is kind of like a consequence that we get, which is if you have f prime equal to g prime for all x in a to b, then f minus g is constant. That is fx equal to gx plus c when c is a constant. So this one is not really helpful right here unless it's if you have two different graphs and try to figure out what is the kind of the slope at these 2 points. But then if not, then this is going to be helpful at the end of the semester when we talk about antiderivative. And then some of the problems that you might be asked in this section is prove that some equations say fx equal to 0 have exactly one real root. So learning about before midterm 1, we have the intermediate value theorem, which allows us to conclude that there will exist at least one root in an interval. But the mean value theorem will allow us to conclude that that root is unique or not. We also have other question asking, say if you have they given us fx and f prime of x smaller than or equal to some value, then you can be asked how large or how small can f some value of f be. They might also be asked if there exists a function f such that fa equal to something and fb equal to something, then f prime of x satisfies something. So it's asking, say this this is one possible, and then I would say this one's equal to example 9 in the lecture notes. So if you guys want to work on it and maybe see, because I feel like that one's really detailed, so I didn't really include one in this review. But yeah, you can always come back to the lecture notes on this. So the first questions we have is question 6 of section 3.2. It's asking if you have fx equal to x cubed minus 2x squared minus 4x plus 2 or negative 2 to 2. Verify that the function satisfies the free hypothesis of Rolle's theorem on the given interval and find all number of c such that satisfy the conclusion of Rolle's theorem. So we have the free hypothesis of Rolle's theorem is that fx has to be continuous. So for sure, this is a polynomial. So I would say fx is continuous because of polynomial. So it's going to be continuous on negative infinity to infinity, which is including negative 2 to 2. Then you have differentiable because it's also like a. So if you take f prime of x, it's just going to be 3x squared minus 4x minus 4, which is also another polynomial, so it is differentiable on negative 2 to 2, or other word is just from negative infinity to infinity. Now we have the last conditions, which is f of negative 2, which is going to equal negative a minus 8 minus plus 8 plus 2, which is going to be negative 6. F of 2 is also going to equal 8 minus 8 plus a minus a plus 2, which is going to be also negative 6. So you have f of negative 2 is going to equal f of 2 equal to negative 6. So all conditions of the Rolle's theorem are satisfied. Now it's asking us to find a number c that satisfies the conclusion of Rolle's theorem. So you have the Rolle's theorem say there will exist at least one value of c in between negative 2 to 2 that you're going to have f prime of c equal to 0. So basically you're just trying to solve 3x squared minus 4x minus 4 equal to 0. And so I will skip the algebra here because it's kind of like very self-explanatory. Or we can maybe try figure this one out, but I will need my calculator for a moment. So if you do the algebra, you're gonna find the two value, x is equal to 2 or x is equal to negative 2 over 3. Yep. So that is gonna be the answer, because if you check back, these two values are in this interval. So you're gonna take both of them and you don't refute any of them at all. So the step is pretty easy. Just make sure that you check the hypothesis for the function if it's satisfied before you actually use that theorem. Now we're going to do the same thing for the second example, where you have fx equal 2 minus absolute value of 2x minus 1. Show that there's no value of c in the interval from 1 to 4 such that f3 minus f0 equal f prime c multiply 3 minus 0. Does it not contradict the mean value theorem? Okay, so the step is the same. We're going to check the conditions. But if we look at this one, this is continuous. Not the continuous. This is a function with absolute value. So as I mentioned in exam 1, we're going to try to break it down into a piecewise functions and try to determine if it's continuous or not. So you have the absolute value is going to equal itself in the parentheses if x is bigger than or equal to half. And then you have it's going to equal to the negative of itself if x is more than or equal to half. or it's then gonna equal to 3 minus 2x with x bigger than or equal to half, and then you have 1 plus 2x if x is smaller than or equal to half. Now, let's see at x equal to half. So you have limit of x approaching half plus of fx is going to be, so it's going to be on the right of half, so which is going to be 3 minus 1, which is 3 minus 2, which is like half, which is going to be 2. Then you do the same thing on the other side. So this is the step that we just try to find if the function satisfies the theorem first before using it, right? So it's gonna be, this is just a 1. It's not -1 or anything. And then this is a negative here, which is going to give us 1 plus 2x, which is, if you plug in half, you're gonna have this equal to 3. Oh, this one also equal to 2. And this one is also equal to half. So we're gonna have f is continuous on 1 to 4. We still have one more conditions to check. So if you have f prime of x, now based on these two functions, we're gonna have this one equal to -2 when x is bigger than half, and it's gonna equal to 2 when x is smaller than half. So basically you just take derivative of these two expressions on the interval at half, because if you look at here, if you want f prime of half to exist, the two values have to equal to one another, but here it doesn't. They don't equal to one another, so you're gonna conclude that f is not differentiable on 1 to 4. And so your conclusion is that it doesn't contradict the mean value theorem at all because the conditions is not satisfying. Now, if you want to check back, show that there's no value of that. So what you're gonna do, you're gonna find f prime of c. Now let's look. What is f3 minus f0. So if you plug 3 and 0 into the equation of fx, you're gonna have 2 minus 6 minus 1 is 5, 2 minus 5 is -4, 3, and then 0 where you're gonna have 1 plus minus 1, which is gonna be -4. So you're gonna need to find f prime of c equal to -4/3 on 1 to 4. But here you can clearly see the fact that you can only have two values of the derivative on this interval. It's either -2 or 2. So you're gonna have no value that's satisfying. So the key things to remember here is always check that you can use these theorem by checking the conditions that they need. Note that each of them have slightly different conclusion. So yeah, that's example 2. So now this is the most important example of this sections, where we get a chance to prove that the given equation has only one real root in the given interval. So as I say, the step to do that is that always we're gonna first use the intermediate value theorem to prove that you have at least one root on that interval, and then the next step is to use the mean value theorem to prove that there's only one root. So we're gonna have f of negative. So you're gonna have f is, to use a mean value, to use the intermediate value theorem, you need f is continuous on 1 to 2, because clearly this is a polynomial, so it's gonna be continuous everywhere. So you're gonna have f of 1 is 2 minus 6 plus 1, which is going to be -3, smaller than 0. Then you have f of 2 is 2 multiplied 8 minus 6 multiplied 2 plus 1, which is going to give us 16 minus 12 is 4 plus 1 is 5, bigger than 0. Then you have, by the intermediate value theorem, you're gonna have fx equal to 0 has at least one real root in the interval from 1 to 2. Now, the next step is to prove the fact that that root is a unique. And so to do that, let's come back to the mean value theorem just to pop for a moment. You have the mean value theorem, let's f be that continuous, and then you're gonna have sure that even got a one real root in the given interval. So I would say here we're gonna use so the way that we're gonna do this is first we're gonna assume that there that root is not unique, and then we're gonna say that that assumption would definitely be wrong, and then we're gonna use it to solve the problem. So we're gonna assume that fx equal to 0 has more than one real root in 1 to 2. So which means that you're gonna have at least two values of C and D that you're gonna have FC equal to FD equal to 0, with C and D belong to 1 and 2. Now, then we're gonna have by Rolle's theorem, and this is usable because you're gonna have the function and also this derivative are continuous and differentiable. So we're gonna have by Rolle's theorem, we're gonna have f prime of E. There will exist a value of E such that f of E equal to fd minus fc, which is gonna equal to 0. But here you look at f prime of x, right? Is equal 3x squared minus 6. Oh, 6x squared minus 6. It's always gonna be bigger than 0 on 1 to 2. Why? If you look at here, you're gonna have 6. If you take the 6 out, it's gonna be x squared minus 1. And x squared minus 1 is always positive from 1 to 2. Therefore, you have this assumption. So this part will never happen. And so this assumption is also wrong. So assumption is wrong. Therefore, we have fx equal to 0 can only have maximum one root on 1 to 2. One real root on, and this is because first you use the intermediate value theorem to prove that they have at least one root, and then the assumption, if you say so when it have at least one root, it can have one root or multiple root. So the second part, we're using Rolle's theorem and mean value, kind of like a general case of mean value theorem, allows us to say, okay, the case of more than one variables is not possible, therefore it can only have at most one variable. It can at most have one real root. So that is all I have for section 3.2. Again, I would say there's a question, I think example 9 in the lecture notes. I think it's really helpful when it's asking us about it's given FA, FB, and then F prime of C, and then it's asking us if there exists such a solution that satisfies it. And so I feel like it's a really helpful exercise to make sure that you understand every aspect of the materials. Now we're going to go ahead to section 3.3. So 3.3 is where we actually touch on the majority of exam 2. So we're going to have increasing, decreasing, the first and the second derivative test, what is concavity and inflection points, and how do we try to find those stuff on for our function, and then later use it to graph our function. Now, first of all, we have increasing and decreasing. So just kind of like definition wise, if you're gonna have an increasing function if you have f prime of x is bigger than 0 on that interval, and then you're gonna say the function is increasing on that interval. and then vice versa for decreasing. And then we have a very important concept for the first derivative test. So the first derivative test say that suppose that you have C is the critical number of a continuous f, and this is, remember last week we find this one by setting either f prime of x equal to 0 or f prime of x does not exist, depending on your type of the solutions. If you have f prime change sign from positive to negative, f has a local maximum. Now it's easy if you just don't try to remember this and just try to graph it out. So if you have f prime change from positive to negative, so when it's positive, it's increasing. So you have it's increasing and then decreasing. So this top will give you the maximum. And the other way around, if you go from a negative slope to a positive slope, so there's going to be definitely a minimum there. And if it doesn't change sign at all, even though it's one of the critical numbers, we're going to conclude that there's no local maximum and minimum at C or on this interval. Next is say we have the definition of what is concavity and how do we find inflection points. So we have definition and concavity test. So if the graph of f lies above all of its tangents on an interval I, then it's called concave upward. So again, graphically, there are two kind of concavity you can think of, either as a U shape or as a reverse U shape. So always when you have a tangent above it, below this, so say here, so you have a tangent below that, so which means the graph is above the tangent, so it's what we call concave upward, or you can remember it as a U shape as for upward. And then below, which is flip of that, is going to be downward. So here you're going to have the tangent above all of the graph, or we're going to say the graph lies below all of its tangent. We also have things called inflection points. If you have a point on the curve of y equal fx, if you have f is continuous there and the curve changes from upward to downward. So say if you have something like this or that, then this point is an inflection point for each of the function here. So once the curves change their concavity, you're going to have an inflection point there. You also have things called the concavity test, which is going to give us if f double prime of x is bigger than 0 for all x, then you're going to have its concave upward, and then concave downward is when it's negative. Another way to think about it is that I usually remember it's like an arrow form where you have like one arrow pointing up and one arrow pointing down. So if it's pointing up, it's going to be upward, and then it's going to upward with the U is going to recall you of the guide of the shape, and then downward is just going down when you have a negative value, and all the tangents lie above the graph. So it's just the way that you try to remember it. We also have a second derivative test. The second derivative test is just give us like some more sense about what is maximum and minimum using both the first and the second derivative. However, this is not very useful when you actually deal with it in the exam, but it can be a really good checked up if you want to see okay, I found it's a maximum and a minimum, but I feel like it's a bit weird. Then the second derivative should be used to check it again. Be careful. If you have f prime of c equal to 0 and the double prime bigger than 0, there's going to be a local minimum. So this is the difference. And if it's negative, it's going to be a maximum. Be careful, the second derivative test is inconclusive. If you have f double prime of x, so the second derivative equal to 0 or does not exist, it wouldn't tell you anything about if there's any extreme values at all. So some of the problems that you might be asked in this section is given a function f, say find maybe a local maximum, minimum, and interval of increase and decrease. So this one is pretty obvious. Find the intervals of concavity and inflection points. Again, this is also easy for the second derivative. Sketch the graph based on the information given by f prime and f double prime. This one is we can try working on this in these sessions, but we're gonna just like a head start. We're gonna look at this one again when we come to section 3.5, and then we're gonna be asking things like how many inflection points does the graph have, and given that expression for f double prime x. Sorry, not explosion. So we're gonna go through I think 3 more example. So it's example 4 is question A of section 3.3. So it's given us this graph, and notice, please read the instruction. It's the graph of the first derivative, and it's not as simply as just the graph of fx like we wanted to. So it's asking us to use this graph to answer the questions. So be careful what you're doing. And I say in these scenarios, when they're asking those things, before you attempt the questions and look at it, try to think about, like, read the question first and try to think, what exactly do I need to find from this graph? What conditions, specific conditions of f prime of x or fx that I need? And then look at the graph so that it doesn't confuse you and you know exactly what you're looking for. So it's asking first, on what interval is f increasing? So you're gonna have f is increasing if you have f prime of x is positive. If you look at this graph over here, it's going to be from 0 to 4 and 6 to 8, because those are the only sections that you have f prime of x above the x-axis, which makes them positive. Then we have b. At what values of x does f have a local maximum or minimum? Now you're gonna have f prime of x. You're gonna have a local maximum. It's gonna have f prime of x to go from positive to negative infinity, and then you have local minimum is the not infinity. It's just negative. It's going from negative to positive. Now to find a local maximum, so you're gonna have local maximum based on the graph here. Is where f prime go from positive to negative. So it's gonna be at x equal to 4 and then x equal to 8. Then you have local minimum is where it go from negative to positive. So negative to positive is x equal to 6. Pretty easy, right? But that's only where you identify what you need to know. So I would highly recommend following that step by just identify the quantity and what exactly do you need to answer the questions before looking at the graph. Now C, on what intervals is f concave upward or concave downward? Now you need f is concave upward when you have f upward is CU. F double prime of x is positive and it's concave downward if f double prime of x is negative. Now if you look at the graph here, f prime, the relationship between f double prime and f prime is that f double prime is just the slope of f prime. So you just try to find the slope of the smaller part. So I would say the slope is positive at from 0 to 1, and you have from 2 to 3. So the slope is going up like this. And then there's also more here. From 5 to 7. And that's it. And then we also have the concave downward. So you're gonna have is from, and this is from 0 to 1. So you're gonna have it's going down. So it's gonna be from 1 to 2, 3 to 4, and then from concave downward. Oh, it's 3 to 5 actually. 3 to 5, and then you have the one coming down from maybe 7 to infinity, I would say, because you don't know where it actually stops, right? And so we also have the inflection points. This is where it go from positive to negative. So it's going to be 1 here. Inflection point is going to be at x equal to 1. From this one to this one. So you have a 2. So you go from positive to negative, and that's in inflection points. And yeah, then we have from 3 to 3. So 3, 5 to 5, and then 7. So you can clearly see here that it's just flipping up and down. And it changed the concavity. Here is concave upward. Oh, this concave downward based on the reverse shape of u, but here is positive, and then this one's negative, this one is positive. So just make sure that you don't confuse yourself with what the question's asking, and try to like identify immediately what you're looking for in the graph, just to save your time, and that's really good practice as well. So we're gonna have the next example is question 12 of section 3.3. So you're given fx equal x over x squared plus 1. Find the intervals on which f is increasing or decreasing. Now, first of all, we're going to look at what is the domain, which is going to be R, because the infinity x squared plus 1 is always positive, regardless of what value of x it is. And you're going to have the first derivative. So let you look at the first question. It's asking us to find the interval of increasing and decreasing. And to do that, the thing we need is the first derivative functions. So you're going to take derivative of this one, which is going to give us x squared plus 1 squared. I'm going to have x squared plus 1 minus x multiplied 2x, which is going to give me 1 minus x squared divided by x squared plus 1 squared. Now we asking to find if it's increasing or decreasing. So again, I would say you don't need to look at the denominator because it's always positive regardless of what happened. So all we care about is the denominator. Now if we set this thing equal to 0 and try to identify what interval is it negative and positive, it's here. You have 1 minus x squared and then x. So it's going to be in 0 at these 2 points, and then it's going to be some value at 0. So it's going to be in between it's going to be positive, and outside it's going to be negative. So the sign of f prime of x is totally depending on 1 minus x squared. Therefore, you're going to have f is increasing on so it's only increasing on the positive part, which is from -1 to 1, and then f is decreasing on -infinity to -1, and from 1 to infinity. So only the negative part that go to infinity. Now we have B. Find the local maximum and minimum values of f. And you can do this one just based on very easy. You can see like this is negative, positive, positive, and then negative. So there's a minimum here and there's a maximum here on the interval form. So we're gonna and the interval of us is from -infinity to positive infinity. We'll try to put it as plus. Therefore, we're gonna try to find what is the value here, which is going to give us f -1 equal to -1 over 2, and then f of 1 is equal to 1 over 2. Therefore, we have this is the local minimum, and this is the local maximum. Therefore, you're gonna have this is the two local maximum and minimum values. Or you can find f prime of x and then try to solve for these two values. But we kind of like did it in part A, so now we only need to care about like how to actually get the numbers based on the graph. So we have that is part A and B. We also have C, find the interval of concavity and the inflection points. Now we have f prime of x is equal to 1 minus x squared divided by x squared plus 1 squared. Now we're going to find a second derivative, which is going to give us x squared plus 1/4. You have -2x multiplied x squared plus 1 minus 1 minus x squared multiplied 2x. Therefore, 2x is the derivative of, we actually need x squared plus 1 squared. And then we need another part of the denominator, multiply 2, multiply x squared plus 1, multiply x, 2x. So it's kind of like getting complicated, but before I do the algebra, I would want you to take a look and try to cancel out something first. And this is what I always do for this kind of exercise. So I'm going to cancel out x squared plus 1 for each side, just to like simplify the expression and make the distribution so much easier. You're going to have negative 1 minus x squared multiplied by x squared plus 1. So you're going to need 4x. And you have x squared plus 1 cubed because I already canceled out 1 earlier. Then what we have is that we have negative 2x cubed, negative 2x plus 4x cubed minus 4x divided by x squared plus 1 cubed, which is going to give us 2x cubed minus 6x. And now we just need to find what value that it changed from positive to negative, or negative to positive. And again, you don't need to care about the denominator because it's always positive. So you just try to solve this one, which is going to give us 2x cubed minus 6x equal to 0. When you try to solve this, you're going to have x squared minus 3, which is going to give us x equal to 0 plus or minus square root of 3. Now make the table. Just want to make sure that they change size. And that was really helpful because I noticed some of the questions in either the practice quiz this week or in the exam, they have something that doesn't change their size, and that can be really tricky. If you just think about it and assume that it's gonna change the sign of f double prime of x. So I would have from negative 3 to 0 to negative 3 to infinity and negative infinity. You're gonna have the 2x multiplied x squared minus 3, or just 2x cubed minus 6x. You're gonna have a 0 here, 0 here, 0 here. And just like try to plug in some numbers and see where it's leading you. So I would say, I think this one is going to be, let me look at my graph. It's question 12 of 3.3. So I have that one is going to be, you have x is going to be negative. So I will put just x squared minus 3. X itself is going to be negative, negative, positive, positive. Then x squared minus 3 is going to be positive, negative, negative, positive. Then you're going to have the entire thing, which is 2x cubed minus 6x, and also the sign of f double prime of x. It's just going to be the product of these two. So plus multiply minus is going to be minus plus negative minus. Yep. So we're gonna have, this is concave downward, concave upward, concave downward, and concave upward, because this is also the signs of f double prime of x. So now that's question 5. If you're watching the video online and if you have any questions, please feel free to email me. No one's actually joining me online right now, so I was trying to like go through the answer. But if you want to just like mute me anytime and work on it, that'll be completely fine. Or ask me questions when you watch it, and just I'll answer them as soon as I can. Now we're gonna have the last example today. So it's question 45 of section 3.3. So you're given a complicated functions with the derivative f prime of x is equal to that. And for what interval is f increasing? So you basically just find the interval of x so that f prime of x is positive. And to do that, we're going to do the same thing as we just did, set out a table like in example 5. So you're going to have, first you identify the values that's going to be put in that value of x. So you need to set this thing equal to 0 and try to find the value of x that make these things equal to 0. So you're going to have x equal -1, 3, and 6. Now let's put the value out. So you have x, negative infinity, -1, 3, 6, and then infinity. Now you're gonna have x plus 1 square, x minus 3 to the 5th, x minus 6 to the 4th, So these are going to be 0 here, and the final factor of fx is going to be 0 at these point. Yeah. So we're gonna have, say, now let's look at our interval. So when you have x plus 1 squared is always positive regardless of where you're going, and the minimum value is just 0, which is at -1 that we already find. You have x minus 3 cubed, x minus 3. Note that here I just find these values by setting each of them individually equal to 0. And this happened because we have the rule saying if you have a product of equal to 0, at least one of them is going to be 0. At least one of the factors is going to be 0. So each of these is a factor. That's how I get those three numbers. So set them equal to 0 individually. If it's already like completely factor like this. You have x minus 3 to the fifth. It's going to be negative when the thing inside of the parenthesis be negative. So you're going to have, and it's only negative when x minus 3 is smaller than 0 or x smaller than 3. So you have negative, negative, and positive, positive. Similarly, x minus 6 to the fourth is the same for the square, the fourth, or the to the sixth power, because all of them is even, and so your expression is going to be positive. So you have positive, 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 positive. Now you're going to put everything together. You're going to have positive, positive, multiply negative, 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 positive, positive. Therefore, you have from 3 to infinity, f is increasing as we want it to be. Note that here you're given the function of f prime of x, not f of x, so please don't try to take derivative. It's gonna take so much time and it doesn't take you anywhere. So I have some practice problems here and also try all of the suggested problem on Canvas. And with that in mind, if you have any questions, please feel free to email me. If not, I'll end the sessions here and I'll see you guys next week. Have a great weekend.